In this video, I'm going to be describing how to use what's called the chain rule, which is just a fancy name for the expanded or full use of the power rule, and we'll see why that is. Using the power rule, we can differentiate x squared and 3x squared plus 1, but how do we differentiate the quantity 3x squared plus 1 all raised to the second power? That's using a composite function or a nested function, and we need a rule in order to differentiate that type of function. So a lot of books will call this the chain rule, and they'll give you this complicated form. They're saying that if we have a nested function or a composite function where we're plugging a function into another, then what you do when you find the derivative is find the derivative of the outermost function or the outermost layer, keep that inside layer or inside function the same, and then multiply by the derivative of that innermost layer or function. Another way we can look at it is using this technique called U substitution. U substitution is a technique that we can use when we're finding derivatives of more complicated functions. So let's introduce it right now because it allows us to simplify the notation of the chain rule. It's still saying take the derivative of the outside function, keep the inside function the same, and then multiply by the derivative of the inside function with a lot less symbols. The trick is to locate or figure out what your layers of the functions are. So in this function, the outermost layer is something cubed or squared, The innermost layer is the quantity 3x squared plus 1. So if you can find those different layers, then we can use this chain rule. The outermost layer was something squared or u squared, since we're using u substitution, and I'm calling u the inside function. So 3x squared plus 1 was the inside function, and it was all being squared. Find the derivatives of each of those layers. The derivative of the inside function 3x squared plus 1 is 6x, and the derivative of the outside layer, u squared, is 2u. So when we plug it back in or use that recipe, the derivative of the outside function was 2 times the inside times the derivative of the inside, which was 6x. And then we can simplify. 2 times 6x on the outside is 12x, and then distribute it through, and we end up with 36x cubed plus 12x. So again, a lot of books will rename this and call it the chain rule, give you a lot of complicated strategies to use it. I think that if we just call it the power rule in its full form, then we're already dealing with something we're familiar with. And the power rule in its full form says that you're going to take the exponent and move it to the front, subtract 1 from the exponent, and then multiply by the derivative of what that root was to begin with. We've never needed to use it in its full form, but this is it. And so if we apply that to this function, then we don't have to memorize a different rule or a different name. It's just the power rule. So let's find the derivative of this function using the power rule. I'm going to take that exponent, move it to the front like normal, subtract 1 from it, and then I'm going to multiply, and this is the new step, multiply by the derivative of the inside function. So the derivative of 3x squared plus 1 is 6x, and then we've reached this step that we got to last time, and we can simplify and write our final derivative answer. So again, just treat it like the power rule in its full form, and then you don't have to memorize a new rule or a new name of a rule. Let's practice doing that with another function. So now I have the quantity x squared plus 1, all cubed. If I want to find the derivative, I use my power rule. I'm going to take my exponent, drop it to the front, subtract 1 from my exponent, and then multiply by the derivative of the inside. So the derivative of x squared plus 1 is 2x. Then I put everything back together. 2x times 3 at the front gives us 6x, and we can leave the remainder, that quantity x squared plus 1, all squared at the end. This also allows us to find the derivative of functions that look like this, where it's a constant divided by a function. This is not the chain rule because the top or the numerator is not a function, so I don't have a function being divided by a function. So if I rewrite this function first, I can then use the power rule. So by using a negative exponent, I can take that denominator up to the top layer and just rewrite it as 2 times the quantity x plus 1 all raised to the negative 1 power. Then I can use my power rule. I'm going to take my exponent, drop it down to the front, multiply by any coefficients, subtract 1 from my exponent, and then the new step, multiply by the derivative of the inside. So the derivative of x plus 1 is just 1. Negative 1 times 2 gave me negative 2 at the front. Put it all together and we end up with negative 2 times the quantity x plus 1. If I have a function nested under a radical, that's another use of this chain rule or the power rule. Again, rewrite this without the radical by using a fractional exponent, and then we can use our power rule. Drop the power down to the front, subtract 1 from that exponent, and then the new step, multiply by the derivative of the inside. So the derivative of 3x squared minus x plus 1 is 6x minus 1. Now we can put it all back together. 2 was in the denominator position. Anything raised to a negative exponent is going to change the position of it, so that whole function is going to drop down to the bottom. 6x minus 1 is going to stay on the top layer. And we could leave it like that. We could have left it in this form using the negative exponent, or we could go back to that radical form and change that fractional exponent of 1/2 back to its square root form. So good luck finding derivatives of nested or composite functions just using the expanded power rule.